Hello everybody, hope you're all doing well and coping with this lockdown. It looks like it's going to last another few weeks anyway, but keep a smile on it. Right, I'm going to go through that tutorial I sent you, and then I'll send you another thing that's got lots of transposition on it, and then I'm going to move on to a bit more curve sketching, find the roots of equations, factorising equations. That's when you multiply brackets out, it's going the other way around. It's going from brackets, from a function to the brackets, and look at simultaneous equations. And also, we're going to look at sine functions and how to draw them. I did a bit of that in the tutorial, and as I say, we're going to look at the roots of equations. That's where they cross the x-axis, and a bit more rearranging and stuff. Okay, so I'll get to that. Okie dokie. I'm going to quickly go through this tutorial. Right, 3x squared plus 4x, and g of x is x plus 2. We want to find f of g of x. So we need to substitute this into here. So we're going to get, I'll do it up here so I've got space, 3 times x plus 2 squared plus 4x plus 2. And 3 times this whole lot, x plus 2 times x plus 2, plus this 4 times x plus 2. Then we multiply these brackets out first. So 3 times x is x squared. X times 2 is 2x, so that's plus 2x to there, and then 2 times x plus 2x, 2 times 2 plus 4, close brackets. Plus we'll multiply this out now, plus 4 times x, so that's that, and then we multiply that as well, 4 times 2, so that's plus 8. Then we multiply all this through with the 3x squared plus, and we add these two together, so that's going to be 4x, 2x plus 2x, 4x, times it by 3 is going to be 12x, plus 4, plus 4x, whoops, plus 8, and that's all going to equal 3x squared plus 16x plus 12. See the 16 and the 8 and the 4 is 12. Okay, now these ones, you multiply brackets out, you do the exact same as what we did there. 2x times x, 2x squared, 2x times 2 plus 4x, 1 times x plus 1x, that'll be, and then 1 times 2 plus 2. And we add all the like terms together, 2x squared plus 5x plus 2. This one here, 3x times 3x, that's going to be 9x squared, minus, because that's a negative, minus 3x times 1, which is 3x, plus 3x, 1 times 3x, and it's a plus here, so that's plus 3x, and 1 times minus 1. Remember, a negative multiplied by a plus positive is a negative, and 1 times 1 is 1. And we'll find that they'll cancel each other out. Minus 3x plus 3x, so that's going to equal 9x squared minus 1. Hope you can see that. Now this one here, x times x, x squared plus 1 times x plus another 1 times x plus 1, because 1 times 1. So that is going to equal x squared is 2x's plus 2x, oops, plus 1. Okay, this one here is simultaneous equations, so I've not got enough room there, so I'll just do it on here. So let's see, you see that 7y plus 5x equals 29, and what is that, 2y plus 10x equals 34. That was the equations of the line from the last tutorial. Right, now, so we want to be able to manipulate these equations so we can get rid of one of the terms. And looking at this, if I was to double this one, so that would be 10x, and I could maybe subtract one of these, and that way make one of these terms disappear with the x term I'll go for. So say I doubled this one, which would be, you see that, 14y plus 10x equals 2958. Now what I could do, this is 12y, say I subtracted, so we'll call this one equation 1, right? This equation 2. So now if I subtract, have equation 1 and I subtract equation 2 from it, that means it would be 14y plus 10x equals 58, and I subtract 12y plus 10x equals 34. So subtracting that from that, and just like a normal kind of sum here, 14 minus 12 is going to be 2y, 10x minus 10x is going to be 0, and 58 minus 34 is going to be 24. Alright, I made a wee mistake there. That should be 2y there, and that would be minus 2y there, so that's going to be 12y. So that's going to equal 12y equals 24, y equals 24 divided by 12, which equals 2. And then we just substitute this back in any one of these equations. Say this one for instance, equation 2, we substitute y for 2, so it's 2 times 2 plus 10x equals 34. So that's 4 plus 10x equals 34. Do what you do at the left hand side is what you do to the right hand side, so I'm going to subtract 4 and subtract 4. They'll cancel, and that leaves 10x equals 34 minus 4, which is 30. X equals 30 over 10 equals 3. And that's simultaneous equations. And if you look back at the question in the other tutorial, you'll find that the point where they intersected, oops, probably more like that, you'll find the x part is 3 and the y part was 4. Okay, going to the next question. Sorry, I meant to say y is 2 there, because y is 2 and y is 3. So if you were to plot that on a graph, or say you'd put plot the points on that, you'd do it like that. You always put the x one first and then y. So that'd be 3 along and 2 up. Okay. This next one here is that was equation of volume that we figured out in the last one. What we're given here is a length and a volume here, and now we want to find out what the radius would be. So we have to do a bit of transposition, then put these values into the equation, and then we can work out what the radius is from that. So that is V equals L pi r squared. L equals 10 meters and V equals 1.9625 meters cubed, so I've got squared there, so it should be cubed because it's a volume. So we look at this, and what you do to the left hand side you do to the right hand side. So we're going to divide this by L pi, the length times pi, and divide this side by the length times pi. These will cancel, so you're left with r squared equals v over the length times pi, and then to find r we get the square root, which means we have to do the square root of L over pi v over L times pi, and the square root of a square, they cancel each other out, so you're just left with r there equals the square root of v over L pi. So let's work that out then. So that's going to be the square root of the volume 1.9625 divided by the length times 3.14, which is pi. And what does that work out at? 2 seconds. That works out at 0.25 meters. Right, and remember when you're doing using your calculator to get the appropriate amount of brackets right and stuff, just to make sure you're going to get the right answer, obviously. Right, now let's see this next question. Kinetic energy, or energy of motion, that is. So the kinetic energy is equal to a half the mass times the velocity squared. Can you see that? There you go. Now say the mass was 15 kilograms and it was going at 5 meters every second. We can work out the energy of that projectile with like a cannonball or something, going quite slow I suppose. So that'd be a half times 5 times 15 squared. No, sorry. So the mass 15, so it'd be 15 times 5 squared. Which is a half times 15 times 25, which equals a half times 375, which equals 187.5 joules. That would have. Now slightly more complicated, what if you were given the EK, say that was, what have I got there, 4,000 joules, and the velocity was 20 meters per second. And so let's see then, we want to find out. So the way I would do this is you've got EK equals a half mv squared. Do to your left hand side what you do to your right hand side. That's half in that, so I'm going to multiply that by 2 to get rid of this 2 there. That means I'm going to double this. They'll cancel, and it leaves you with 2ek equals mv squared. We want to know what m is, so divide that by v squared. Do the same to the other side. So the mass is going to equal 2 times the energy divided by the velocity squared, which equals 2 times 4,000 divided by 20 squared. So that's 8 thousands divided by 400. Is that right? That's 400. So straight away you can say they'll cancel. It's like 80 divided by 4, which so happens to equal 20, the same as 20 kilograms. I'll just check that just to make sure I've done that right. That's right, it was just a fluke. I just made those numbers up. Right, now what I'm going to look at here is probably the most important one. I don't know if you can read my writing there. It was draw the graph of y sin x, y 2 sin x and y sin 2x and put them on the same graph. I'm just going to do that just now. Right, we're going to draw the function y equals sine x, y equals 2 sine x, y equals sine 2x, and y equals sine a half x actually. And we're going to go up in 30-degree steps, and from 0 to 360 is going to, it's one full cycle, and I'll show you what I mean in a second. Right, sine yx, and this is basically all you're doing is saying to yourself, can you see that, my calculator? I think you can see it there actually. It's very bright. I'll bring the brightness down. I don't know if that's better. Aye, that's much better. Right, basically what you're doing, see for this one here, the sine of 30, you're just putting in the sine of 30. So that gives you 0.5. So we look at that, there's 3 spaces to get to 1. I'm just trying to draw it to as scale as possible, so this will be halfway, about there somewhere. The next one, I'm not going to split this, then the next one's just going to be the sine of 60 equals 0.866, you see that? And 0.866 is 2.54 spaces, so about there somewhere. And then when we get to 90 degrees, the sine of 90 is actually 1. And then when you go on to 120, it starts dropping back down to the same value as that, 0.866. Here at 150 it gets to a half again, and at 180 it's sitting at 0. And then as we move along another 30 degrees, that goes to a half again, like that. This one here goes up to 0.8, what was it, 2.5, it's 0.866. 270 goes up to 1, and so forth. And back down to 360, which is 0. And if you to draw that out, just lightly sketch it, you get this shape, which we've seen many times looking at AC electricity, and that would be one cycle of AC electricity. If that was 50 Hertz, that means that would be happening 50 times every second. And 50 times in a second, that means that would be happening in every 0.02 seconds. So it's pretty quick. Now what we're going to do now is I'm going to do y equals 2 sine x, and basically what that is, see this point there, it's a half, and go 2 times a half is 1, so it's going to be sitting up there. 2 times this one is going to be up here. The 90, 2 times that is going to be up at 2. And basically what this is doing is this is just doubling whatever value you've got there. Back down to here, there, then 0, 2 times 0, 0. Again this one here up to a half, up to here, up to there, up to there, down to there. And if you draw this one out, we'll draw it from this angle. Maybe not the best of drawings. So you can see what the difference that's made to this function. It's doubled it. Now this is actually when we're talking about AC electricity or any cycles or any cyclic kind of maybe a radio signal or something like that, this part here we call this the amplitude, and this is like the say you were getting a radio signal and you were getting this one, or you were getting this one. They're exactly the same frequency. The only thing is this one's twice as powerful because it's got twice the amplitude. Does that make sense? And obviously if that was a half in front of that, it would kind of look like that. It would be a smaller function. And I suppose you could also say if that's electricity, that's going to be 1 volt, that's going to be 2 volts, that's going to be half a volt. Peak, that's your peak voltage. And obviously you'd have your AC signal. Remember this is minus, so that's -1 and -2 there. Now I'm going to show you what the difference here makes. Right? Now what this is doing is this is saying if this is 30, 2 times 30 is going to be 60. So the value you would have put at this point, the 60 here, you put that in there. I'll put this in wee crosses or something. So that would be like that. And let's have a wee think about this. So then, actually that's right, so it would actually reach, so 2 times 45 is going to be where it's at in 90, so it's going to be there, and it's got a 60, it's going to be, well, it will be at 120, so that's there. I don't know if you can hear the rain. And then at 90 is what it's going to be at 180, so that's coming through there. And then up here it's going to be at 1 again, and these other ones here at the 120 is a half of that, wasn't it? And this one was a half. So if we draw this one out, you see what's happening there. Instead of having the cycle taking 360 degrees, this is actually cycled right round to the start again in 180 degrees. So in other words, this has doubled the frequency of how quick it goes in a cycle. Or if we were to half that, let's say let's half it from here onwards. So we were saying that so that would be like 30 degrees was a halfway up there, but that would only be half that then. 240 is going up to there, but it's only half that. 270, you're sitting at 3 seconds. So I've drawn that in there. So whereas here it was 30 degrees to get to halfway, see that? But in this situation where it halves the value, it's going to take you 60 degrees to get to this value, and that's that there. And this one higher up there, remember we're kind of looking at this one, right? So to get to that value, instead of taking 60 degrees, instead of taking 60 degrees, it's going to take 120 degrees. And then to get to this point here, which was 90 degrees, that's actually going to take 180 degrees. And then, so that means if that was moved back to there, that was only doing a half a cycle in the full 360 degrees. Just like what it says there, the sine y equals sine a half of x. So what I want you to get from this is this number here determines the size of the amplitude, and this value in front of the x here determines at what rate it traverses this axis, or at what rate it goes through its cycles. Now say even like each one of these was 1 second, so that first signal there would take 12 seconds. So a way you could sort of describe that would be it would go round 5 times. This would do it 5 times in a minute, and you could say, well, that would be 5 revolutions per minute, because it's taking 12 seconds to do 1 revolution. See, that was a record. It would take 12 seconds to go round, and that means it would go round 5 times every minute. What was old LPs used to be? The old vinyls, 33.5. And what was an LP? I mean a single. Can't remember what a single was. Is it 64 or something? Can't remember. Some of you will remember that. Some of you might remember the old gramophones. Right, so that's that. I hope that made sense, and cheers for listening. Right, we were talking about brackets, and say we had a function y equals 3x squared plus 2x. Hope you can see that there. And it's, what I'm going to do is I'm going to just kind of roughly draw what that would look like. I'll just do that now. Right, I've quickly done some calculations here. Right, and this is this 3x squared plus 2x. Oops, don't know if you can see that. Hope that's clear. Right, now what I realised looking at it is when you get beyond 1 and 2 it becomes a very large number. When you get beyond -2, -1, along it goes. So, and what I did work out there, that 1, if you put 1 into there, that gives you 5. So see you goes, see you put 1, so that's y equals 3x plus 2x. If you put 1 in there, that'll give you 3 times 1 squared, which is 3, plus 2 times 1, so y is going to be 5. If you put 2 in there, that goes up to I think it was 11, because that would be 9, so that would be 2 would be 4, 12, no, that would be 16 actually, that goes up to. So this kind of goes like that. That's going away off to infinity, I suppose. The bigger that gets, the bigger that will get. Now, after here, right, if you put in minus 0.175 in there, or say, well, see you put minus 1 in there, that will give you 3 plus 2 times minus 1, which leaves you 1, right? If you put in minus 0.75, you get 0.2825, which should be about there. If you put in minus 0.5, what I've done there, you get 0.75 minus 1, which equals minus 0.025, which is, I could have drawn this a little bit bigger I suppose, but you can see that wee x here, it's quite a small value. And then looking at 0.25, sorry, I've done the scale so it's 0.25, 0.5, 0.75, then 1, and here I've got minus 0.25, minus 0.5, minus 0.75, minus 1. So we're here at minus 0.5. If you put that into the equation there, yeah, it comes out at minus 0.25, which is there. And at minus 0.25, we get to minus 0.3125, which is slightly bigger. And then what I did is I just quickly checked in between there, which is minus 0.125. And when you plug that into this equation there, you get minus 0.2. So what you can see is happening there, if you were going to join these points together, it's kind of going like that. And we know this crosses this axis at 0, because if you put 0 into there, you get a 0y value. Now, if we want to, one of the things when you're an engineer is a lot of times this might be a kind of threshold for maybe temperature or the maximum amount of current you can give an induction motor or something like that, or some sort of system where it is required to be above this axis. And this is a function of whatever system you're using. See, like the electrical current use from a motor, and see that was your torque or something like that. Now, what it is very useful at times is to find out where this equation cuts the x-axis. And we will find it cuts the x-axis is where this equals 0. See, if you set that to 0, you can find out at what value of x it equals 0. And that is useful, as I say. That could be the limits to your temperature in an air conditioning system, anything like that. Now, we could just keep plotting in the values there, which you could take. It's time consuming, might not even be accurate, you might never get to the bang on bit. But there is a way of using algebra to solve this, funnily enough. Right, I'm going to show you how to solve it. What we want to find out is where it's cutting the x-axis round about wherever this is going to be, and we suspect, we know it cuts it there, but I'll just kind of prove that. Now you get, this is what they call factorization. It's finding out the different factors from the given function. Now this one is y equals 3x squared plus 2x. Right, and we want to make that equal to 0 to find the roots of the equation. Right, now you can, well, in this particular equation, right, I'm just going to show you, and then I'll show you how it's the right answer, and then we'll just do more examples, and then it will start hopefully formulating itself inside your head. So what's the common factor between these two? I'll rewrite that. 3x squared plus 2x equals 0. The common factor there is x in both these terms. So I could rewrite that as x times 3x plus 2 equals 0. Now we know, see if that equals 0, that means that's all going to equal 0. Or if that equals 0, that means all that's, well, I mean the answer is going to be 0. So for instance, so in this situation we can say that one of the values for x as a root must be 0. Right, and as I say, I'm just going to show you that just to show you how it's done, and then hopefully the more examples you do, the more it will start making sense in your head. Because if that was 0 and x was 0 there, you'd get 0. Right, but what we can do as well is we can say then, because we've already accounted for what this x is, this root of this x, we can say 3x plus 2 equals 0, and 3x equals minus 2, x then equals minus 2 over 3, which equals minus 0.667. So looking at that equation again, we can't see it exactly. That's 0.5, that's minus 0.75, that's minus 0.5, minus 666 would be round about there somewhere, and the 0 again where it cuts the x-axis. Right, now I'm going to do another quick one just to give you an idea of how you can quickly establish what a graph would look like. We've got y equals x squared minus 4. Right, now we know that the equation will cut the y-axis when x equals 0, and the same type of thing when this equals 0, we can find where it cuts the x-axis. So say we substitute 0 into there, in other words at this point here where x is 0, y is going to equal minus 4. Now the next thing I would do, or what we're going to do, is find out where it cuts the x-axis. And I was saying to you that if we make y equals 0, so that means 0 equals x squared minus 4, and we can rearrange that. Plus 4 on this side, do to the same to the other side, so x squared equals 4. So x then is going to equal the square root of 4, which is, I don't know if you've came across this yet, if you multiply a negative by a negative, you get a positive, and if you multiply a positive by a positive, you get a positive. That kind of works backwards when you're looking at a square root, because the square root of 4 is going to be plus 2, but is also going to be minus 2, because if you multiply 2 by 2 you'll get 4, and if you multiply minus 2 you'll get 4. So when you've got x equals root 4, that's telling you there's actually 2 roots, and what that's going to be is plus 2 and minus 2. So I know instantly that equations, that function is kind of going to go look like that. Now these are kind of quite simple examples. I'm going to do another harder one where I factorise and you get brackets. Right, I've got a bit more complicated one here. Y equals 2x squared minus x plus 15. Right, we want to do a rough sketch of this. Right, to do a rough sketch we'll find where it cuts the y-axis and we'll find where it cuts the x-axis. So it cuts the y-axis. Where's it cut the y-axis again? Yep, that's right, x equals 0. Glad you said that. So y equals 20 squared minus 0 plus 15. So it's going to cut y at 15 plus 15. Now let's see, we want to know where it cuts the x-axis now. Right, so let's have a look at this. We've got excuse me, we've got another one here. Y equals 2x squared minus x minus 15. We want to do a quick rough sketch. Easiest way to do that is to find where it lands on the y-axis and where it lands on the x-axis. I'm not drawing it to scale or anything like that, I'm just roughing it. So how do we find where it lies on the y-axis? How do we do that again? Oh, that's right, I put x equals to 0. I'm glad you said that. So y equals 20 squared minus 0 minus 15. So that's 0, so y equals minus 15 when x equals 0. So say that's going to be down here, so minus 15. Right. Now we want to find out where it cuts the x-axis. I remember on the last one it was what was it, 3x squared minus 2x or something like that. We brought it about 3 x minus 2 equals 0. Right, this is slightly different, but it's using the same kind of principle. That is kind of like the same as another bracket with x plus 0 times 3x minus 2. I'll show you what I mean. Hopefully this will make sense. Now what we want to do is split this up into the brackets it was made up of in the first place. This can be quite tricky actually. This one's maybe quite hard. Now I know it's going to be 2x there, and this other bracket is going to be x. Because that last number's a minus, I know whatever number's multiplied that last number there, there must be a plus and a minus there. I'm not sure which one as of yet. Now if we have right, so I know there's going to be a 3, one of these is going to be a 3, one's going to be a 5 because you get 15 there, and one is going to be negative, and see how you get 1 there, because you add these values and there's a 2. If we've got a 3 there must be a 6 there must be a 3, that must be there actually, minus 3, and that'll be plus 5. It's easy for me, I've done it for years. So that would be, if you multiply that through, that would be 2x squared minus 6x, then this one would be plus 5x minus 15. So that's 2x squared minus 6x plus 5x equals minus x minus 15. I know that's quite tricky, that, and you have to practice these. I'm going to send you a tutorial with a few of these on it, and practice them. That one admittedly is quite hard, I suppose, but what that means is we can say, if we want to find where it cuts the x-axis, we would say 2x plus 5 times x minus 3 equals 0. And we can split these up into two separate ones now. X minus 3 equals 0, which means that x equals 3. So we know now it cuts the x-axis at plus 3, that's one of the roots. And now this one, 2x plus 5 equals 0, x equals minus 5 over 2, so x equals minus 2.5. So that'll go over here somewhere. Minus 2.5, and that's 3. So that's going to go like that, something like that. Can you see that? Good stuff. Right, going back to the equation earlier, this y equals 2x squared minus x minus 15, and the roots were x equals 3 and x equals minus 2.5. Right, can you see that? There we go. Right, now I'm going to just illustrate something here, and the fact is that sometimes you get equations, maybe see if that was 0.0725, that was minus 1.8925, and that was an odd number. It's impossible to factorise them in whole numbers as such. So some bright spark came up with this equation years ago. X equals minus b, then it's plus or minus b squared minus 4ac divided by 2a. And see if you can't factorise an equation like that, or function, you just plug these values into it. Now what we mean by this though is, so what you've got is here is a variable a, b and c. Yeah, okay, what are they? Right, when you have an equation and you've got, it's kind of like a x squared plus bx plus c, where if this was 3x squared plus 7x plus 3, ABC would be 3, 7 and 3. This number represents the number that's in front, or the coefficient they call it, of this value, of the x of the squared values. The b represents the number of the non-squared x values, and c is just the number left at the end there. So again, if that was 4x squared plus 12x say plus 4, again a would be 4, b would be 12 and c would be 4. So to illustrate this, I'm just going to put these values into there and we should get the same as that. So x equals, and see how you get your, this is why this has got a plus and a minus there, because the root is always minus b, then it's either plus b squared minus 4ac over 2a, or it's minus b minus that value divided by 2a. So the first one is going to be minus b b. So this one here we've got, can you see that up there? This is going to be 2, that's going to be minus 1, that's going to be minus 15. So minus 1, and we'll go for the plus one first. Plus minus 1 squared minus 4 times 2 times minus 15, all divided by 2 times a, which is 4. So that's plus 1 plus, let's see, the square root of, so it's going to be 1 minus 4 times 2 times minus 120, 80, that's minus 120, so that's going to be plus 1 plus the square root of 119, all divided by 4. How does that work out? That hasn't worked out right. I'll just check that. So what you've got is there is a variable a, b and c. Yeah, okay, what are they? Right, when you have an equation and you've got, it's kind of like a x squared plus bx plus c, where if this was 3x squared plus 7x plus 3, a, b, c would be 3, 7 and 3. This number represents the number that's in front, or the coefficient they call it, of this value, of the x of the squared values. The b represents the number of the non-squared x values, and c is just the number left at the end there. So again, if that was 4x squared plus 12x say plus 4, again a would be 4, b would be 12 and c would be 4. So to illustrate this, I'm just going to put these values into there and we should get the same as that. So x equals, and see how you get your, this is why this has got a plus and a minus there, because the root is always minus b, then it's either plus b squared minus 4ac over 2a, or it's minus b minus that value divided by 2a. So the first one is going to be minus b b. So this one, and this one here we've got, can we see that up there? This is going to be 2, that's going to be minus 1, that's going to be minus 15. So minus 1, and we'll go for the plus 1 first. Plus minus 1 squared minus 4 times 2 times minus 15, all divided by 2 times a, which is 4. So that's plus 1 plus, let's see, the square root of, so it's going to be 1 minus, let's see, 4 times 2 times minus 120, 80, that's minus 120, so that's going to be plus 1 plus the square root of 119, all divided by 4. How does that work out? That hasn't worked out right. I'll just check that. Plus 1 minus 11, again that's going to be 11 over 4, which is going to be minus 10 over 4, which is minus 2.5, which was the other root up there. So I think we've done quite a bit today, I think. I don't know if you've got this thing. I'm sure some of you have. If you haven't got it, I'll send it to you, and it's quite handy for practicing your transposition. I'm going to send you another tutorial with this, and it's kind of covering what we've done today in the last tutorial, but also it maybe goes a little bit further. But I'm wanting you to have a go at the questions, and you think you're equipped enough. Wait there. Aye, I want you to have a go at the questions. I think you're equipped enough to be able to handle them, and if you can do them, do the tutorial and send it back to me, and I can use that as evidence of how you've been getting on and stuff. Okay, right, thanks for listening, and I'll send you another lecture next week. Okay, take it easy, bye.